Okay, unfortunately, unzipping the images and compiling the original LDSO at the same time just crashed my stream, so I had to restart. But I took the time and investigated the reason for the ZipLib, and I found what the problem is with the ZipLib. So let's talk about that now. So when I compile here, I get the message that ZipLib is not found. And I have found out that the reason for that is that in my CMakeLists file, that is the one in the root directory, the find package command is looking for libzip in capital letters. However, in the CMake folder, there is a CMake file called find libzip with a capital L, IB, and a capital Z, IP. So if I rewrite it this way and save that again and recompile the project using MakeProject.sh, then we will see, hopefully, if we scroll up, that now ZipLib has been found. We have this other warning, which is new, which is about this libzip that, it's looking for capital libzip, but it's not finding it and stuff. But this can probably be fixed by looking into this find libzip.cmake file. But it's working, and as you may know, never touch a running system. Let's keep it like that for now. Okay, this way we should be able to load in the zip directory. I still have extracted the archive here for the dataset into this images folder, which you can see here. So these are the images, but in this file here, we are still looking for the images.zip file. So let's keep it like that, and let's test if this is working. This is something I did not test. But anyway, also the original LDSO code base is compiling as expected. So this helped me to fix the error with the libzip. Let's now, this has compiled, so let's now run the code again, or the algorithm. And now we have a nice yellow warning, which tells us I need higher resolution. I will probably segfault, but there is no segfault. Okay, so in this global calib, we have the result that the algorithm is using pyramid levels 0 to 0, which is weird. And the causes resolution is also wrong. So something is going wrong here, clearly. Which could be due to the missing loading or storing of images. Let's see. Let's check the code into the dataset reader, and let's see what is happening here. So when we are creating an image folder reader, we are going through the path, checking if it is zipped. So actually this should be not grayed out because we have the ZipLib here. And it's going through the directory and telling us that it got X entries and Y files. Let's see. Got 3000 images. Where is this printed? This is not printed at all, which is weird. Ah, here, okay. Got 3000 entries and 3000 files. So this is okay. So this works. What happens after that is we need the undistorter. We do not have the undistorter. So this is not being done, and so we do not get the width and the height of the images. So this is probably the problematic part and the reason why it's not working the way it should. That's a pity. Because here, from the undistorter, we get the calibration matrix K and the width and the height, it seems. And we need that. We do not get the parameters at the moment, unfortunately. Which means, yeah, that's the reason. So this is call by name, but the parameters are not set. Therefore, we pass obviously 0 here, and this cannot work the way it is right now. So we desperately need this undistorter, which we can only get when we implement the image file formats. And to have the image file formats, we need to implement the global funcs. I think we do not really need them right now. But once we are at that, in the internal directory, like here, we should probably just finish that. And then slowly we can get to the image read-write, image and exposure, and undistort. Yeah, so we need to invest a little bit more time, and we do that by finishing the global funcs header file now. Okay, so let's continue where we have left off without talking too much. And just writing down on this file. So we need the global funcs header file. And we are here. And now we start with the traditional pragma once and the include guards, if not defined, LDSO Twitch, global funcs H. Then we define that. And in the end, we want to end the if for the include guards. Okay, here we also want to include the previously created numtypes.h file. And we also want to use the namespace for the LDSO. And we also use the namespace internal here. Maybe for the explanation, what we will do here, this global funcs header file will contain, as the name says, the global functions, which are used in the DSO, so the direct sparse odometry, namely for interpolation and visualizations. What do we mean by interpolation? If we have this residual pattern from the paper, this one in figure 4, then we might have a situation where the pixel grid will not be ideally structured. That is, we might need a color that is in between 2 pixels. And if we have such a situation, we need to interpolate between those cells. We have a linear interpolation between 2 cells, we have a bilinear interpolation between 4 cells, we have cubic interpolation and so on and so forth, and this logic needs to be implemented. This is for the interpolation part. For the visualization part, we need to generate colors usually. Colors in like this, for example, as you can see here. So this is like a heat map, or like this cold to hot color scale. There is a jet color scale, there is a rainbow color scale. For visualization, we need to provide those colors. And those are the 2 main parts that are included in this global funcs header file. So interpolation, let's write it down with linear, bilinear, cubic, and so on. Visualization is rainbow, jet, color ramps, for example. That is, for example. Okay, let's start. There is something else here, namely, if we have a vector, we might need to do operations on vectors. Vector operations, removing an element, for example, from a standard vector. And this will be done in this first part of the internal functions. For this, we define a template where we have a specific type name written as t, and we define an inline function of type void, which we call delete out. We pass a standard vector of this type t, a pointer, and this is usually our vector, as the name already suggests. And we have a constant int I, which is probably the index. And now in this header file, we also directly add this implementation in line. And the implementation will say, we take the vector at position I and set it to the vector at the back. So we take the last element of the vector and put it at position I. This way we will keep that value, and we can now go ahead and call vPopBack, which will delete the last element. So this is one version. We need another version, which is also called delete out, but it has a different argument list. So here we take a vector, a standard vector of type shared pointer, which is of course a pointer of this t type, but the rest will stay the same, and also the implementation will stay the same. we have another delete out variant, which starts in the same way as the one here above. But now takes not a constant integer, but a constant shared pointer of type t, where we have a reference to e. And now it gets a little bit more complicated, because now we have to loop through this vector. So we have a for loop, we have a shared pointer, of type t, and we loop through this vector v, and here in each iteration we check if t is equal to e. If this is the case, we save the t, which is equal to v times back. We take it from the back of the vector, the last element, store it in t, and once again we call v.pop back, and then we break the loop. And the rest is not needed here, because this is already inside. Okay, next we have another function which is called delete out order, which takes in a standard vector of a simple type t. And then we have a constant template type t, and then element. In the function body we store a variable int I equals -1. Then we loop through the vector by typing unsigned int k equals 0. K is less than vector size, and k plus plus. Then we check if the vector at this position k, or this index k, is equal to element which was passed into this function. Then we say I equals k, and we break the loop. After this for loop, we assert the value of I. We check, is it still equal to -1? Assert, not assert. We assert it. And if this still continues, then we have another for loop. Which loops through using an unsigned int called k. This starts at I plus 1. And loops through while k is less than v.size. And then we increment k. And in the body of this loop, we say v at position k minus 1 is equal to v at position k. So the previous element is basically the current element. After this for loop has been completed, we say v.popback. So we delete the last element, but this time we take into account the order of the elements. Okay. This is so far the preparation, or like the vector operations part. Next we have our interpolations. And as a first function, we have a function that reads an interpolated element from a float array. This will be an important function because this will be called over and over again. We start with an optimization macro, which is the eigen always inline macro. Then we write float, and then below we say get interpolated element. This function takes in a const float pointer to a const mat. So we take in a matrix, basically an image or a part of an image, a const float x, const float y, const int width, and const int height, I think. No, the height is not necessary, I think. Yes, the height was imagined by me, by myself. We do not need that because we can simply work with the width, given that we have correct values for x and y, as we will see in a minute. So here first we get the integer values of our x and y coordinates. So we define an integer ix is equal to cast to int x, and we get the integer y by casting y to the integer. Next we have two floats for dx, which is equal to x minus ix. So this is the delta portion. Float dy is equal to y minus yi, or I y. Next we have the float dx dy, which is equal to dx times dy. And then we have a const float pointer bp, which is equal to the matrix plus ix plus iy times width. What looks cryptic here is basically if we have an image, we have the x values here, which tells us at which column are we currently, and then we have a total width of this image, so this is filled up with some other values, and by adding the y values we can get to some other point, for example. So we can fill up here the remaining the remaining space until we get lower and lower in the image, and then are here or something like this. So I hope you understand what I mean. This is just some fancy pointer arithmetic, which allows us to get the memory address here, add some step through the memory address in the computer, and then we get to some other memory address. We store that in this pointer so that we can later access the value that this pointer is pointing to in the memory and into the memory. Okay, so once we have calculated the position in the image, let's say this is the image idea. To access a specific pixel value. Next, we want to calculate a result. Load res is equal to, and now there's some fancy magic here, dx dy times bp at 1 plus width plus, let's write it in the next line, plus dy minus dx dy times bp at width plus dx minus dx dy times bp at 1 plus 1 minus dx minus dy plus dx dy times bp at 0. After calculating this this result, return the result. Return res, and this is it. So this looks maybe a bit confusing, but we are actually saying we want to take at the current position BP. So at this pixel, we take some parts from the left, some parts from the right, and some parts from other elements from the image, and we make a mix out of that, and we return that. And now in this file we have several of those kind of types for interpolating values, and we will implement them now. So we can now copy that part and paste it again. I will delete this comment. And what we'll change now is we'll change the comment here. We say get interpolated value from vector for f mat So now we have a 4D vector composed into a matrix, and we return interpolated vector 3f by throwing away the last dimension. So this could be something like an RGBA image, where we just want to get the RGB values, the red, green and blue values, for example. I'm not sure if this is the case here in this code. We can only find out when we implement the usage of that, but now we need to prepare that. The return type is a vector of 3f, as the comment already suggests. Vector 3f. We have defined that using the numtypes header file. Now the input is, as the comment also suggests, from eigen, a vector 4f, const mat. We have a const float x, a const float y, and a const int width. Then we get the integer values again. We calculate the delta x, the delta y, and dx dy. But now we have a constant eigen vector 4f bp, which is equal to mat plus ix plus iy times width. And now we have the result, which is a eigenvector of 3f and that is dx dy times, and now once again we have a times in parentheses const eigen vector 3f and then bp plus 1 plus width plus dy minus dx dy times, and then once again the vector. Oh, I forgot a star here, an asterisk. So times the pointer of const eigenvector 3f pointer, and then we have bp plus width, then plus dx minus dx dy. Once again we need that pointer here, and here we have bp plus 1. Very cryptic. And the last line is plus 1 minus dx minus dy plus dx dy. And then once again we need that pointer. And then bp. And then we return that res. And that's it. Now there are still many of those variants. We copy that now. And here we get the interpolated value from a vector 3f mat. and the return value is still the same. So I will now leave that here, turn interpolated vector 3f, but we are not throwing away a dimension, of course. So now we need to change the input is a vector 3f, mat, x, y, and width are still the same. Then we have the integer x, integer y, dx, dy, dx, dy, and here we have a vector 3f. BP is equals to mat times ix plus iy times width, and the result is a vector 3f, which is dx dy times eigenvector 3f, bp plus 1 plus width, dy minus dx dy, vector 3f, bp plus width, dx minus dx dy, 1 minus dx minus dy plus dx dy. That's fine. Next, we copy that function and paste it again. Now we have an interpolation with and mask. Oh, and I forgot that we are renaming the functions here. So the first one is still get interpolated element, but the other two are called get interpolated element for 3. So we convert. No, I scrolled too much, sorry. So the next one is for 3. So we take a vector 4 and convert it to a vector 3. So get interpolated element for 3. And after that, we have get interpolated element 3, 3, because we take a vector 3 and convert it to a vector 3. With this and mask, we want to return still a vector 3f, but the function is called get interpolated element 3, 3 over and. Here we take an eigen vector 3f const mat. Next we have a const bool pointer called overmat. Then we have a const float x still. I will move that to another line. Const float x, const float y, and a const int width, but also a bool with a reference to over out. Okay, seems more complicated. Let's see how this is implemented. We have the integer x, integer y. We have a dx, dy, and we have our dx, dy, which is still the same. Next, we create a vector 3f, bp equals mat. This is the same. But now we also create the bools, const bool b star bbp is equal to overmat plus ix plus iy times width, and the over out is equal to bpp add 1 plus width and BBP 1 and BBP width and BBP 0, so that we can return basically the same, it seems. This is still the same. Yeah, this did not change. Minus the xdy. Okay, and we return that result. Okay, wasn't that complicated. We can now get to the next one. So we copy that. We paste it. And now we have not the AND mask, but we have the OR mask. So we rename that from AND to OR. We still have the same matrix. We have an overmat. We have X, Y, width, and we have over out. Then we still have the integer parts here. Then we have a vector 3f, which is still constructed the same way as before. Now next we have the bool BBP is equal to overmat plus ix plus iy times width, and over out is now BBP 1 plus width. And now we need to replace these ands here with the OR operator. So those two pipes. But the rest is still the same. So it seems to be easy. Let me double check if this last part has changed. To 3f. This is the same. This is also the same. This is identical. Okay, that's fine. We can leave that and copy it again. And paste it here. And now, unfortunately, there's no comment. But the return type is now once again a float. We say get interpolated element 3,1. We pass in a 3D matrix without the overmat, with x and y const floats, and the width without the last bool. Then we once again get the integer part of that x and y, the delta, the dx dy, bp equals mat plus. This is fine. We can get rid of these bool calculations. And next we return dx dy times parentheses. This whole part, bp1 plus width. Then we close the parentheses and x is the 0th element. And we do that for all the parts. So I copy and paste this closing parentheses with the 0 element access and add the opening parentheses here. And this should be okay. Next, we copy that part again. And this is a bit boring, I'm sorry. But those are different ways to get the interpolated elements. So next we do not get a float. Oh, I think I made a mistake. It's really easy to make a mistake because this one here returns a float. But this is still a vector 3f, but this here should be a float, obviously. So this one should be a float. It's really hard to get confused here, or really easy to get confused, I mean. But for the next function, we return not a float, but once again an eigenvector 3f. And we rename that function to get interpolated element 1,3 by lin, which is probably a short form for bilinear interpolation. And now the input is not a vector 3f, but a float. So this could be a grayscale image. X, Y, and width are still the same. Then we take the integer parts of X and Y and we postpone the delta calculations, because first we want to calculate this BP. I copy that from here. This is a float. Float BP equals mat plus IX plus IY times width. This is the same as before. But now we have some additional variables. Float TL is equal to star of BP, semicolon. So this is probably top left. We now calculate the 4 neighbors. So this is the top right, and we have bottom left and bottom right. This is BP plus 1, BP plus width, and BP plus width plus 1. So this is top right, bottom left, and bottom right. Then we calculate delta x the same way, delta y, and we have 4 new variables. Float top int is equal to dx times tr plus 1 minus dx times tl. Then we have a bot integer, a left integer, and a right integer. So top int is correct. Bot is bottom right plus 1 minus the x times bottom left. So this is the second parse, let's say. The second linear interpolation, we could think of that. dy times bl plus 1 minus dy times tl, and then dy times br plus 1 minus dx, no, dy times tr. Then we want to return an eigenvector 3f. Can get rid of this line. And this res is calculated by dx times right int plus 1 minus dx times left int let's get rid of the rest here. Then we have right int minus left int and bot int minus top int. Let's just define it with the constructor like this and return the rest. Let me double check. The x right int. Okay. Can add some new lines here to make it easier to read. And then this should be fine. Next we have the same function. So we copy that with a different name and some little modifications. So we return a vector 3f, but we get not a float, but an eigenvector 3f, const mat. Then we have x, y, and width once again. Then we get the integer parts. We calculate a const eigenvector 3f. bp equals mat ix, iy, width. This is the same. Then we calculate the floats as before, but now we have to take the first element. So we put parentheses around this expression and take the 0th element. Like this. Then we have dx, dy, which is the same. Top int, which is also the same. So this is okay. And then we return a vector 3f, which consists of dx times right int plus 1 minus dx times left int, right int minus left int, bot int minus top int. And then we return that. Okay, that's fine. Let's copy that once again. If you're staying with me, I have to say that I have a big respect because I'm starting to get tired from that, but it's fine. Okay, now we have the same return type, vector3f, but now we have a function name with 33 by lin. So this is, as the name suggests, getting a vector3 matrix and returning a vector3. So we have x, y, and width still. We get the integer parts. This is the same. This is also the same. The x dy is also the same. Top int. This is also the same as before. And now let's see about the vector. Dx times right int plus 1 minus dx times left int. Right int minus left int. Bot int minus top int. This is weirdly the same. Seems like I made a mistake somewhere. Okay, I think I know where. So here in the function above, we expect a 1D matrix, like a grayscale image, for example. And I have this eigenvector 3f here, which is wrong. So let's rewrite that to a float. And then, of course, this one here needs to be a float as well. And here we need to get rid of this 0. Like this. The parentheses need to be gone as well. Okay. And we return a vector 3f. So this is fine. Okay. I think I got myself confused here a little bit. Let me quickly check that. I'm sorry about that. So this is 3.1. This is okay. This is 1.3 by lin. This is also okay. Then I have 1.3 by lin again. But I should have a 3.3 by lin, which comes later. So I think I can delete this one. Float and 3f. 3f. Okay. Okay, we should be fine now again. It's really the possibility that I mixed up something which will not work later. And in this case, I'm curious if I can fix it. This will be hard. But I think it's fine. So let's copy that and paste it again. And now we have another function that is as follows. We return a float. We name the function getInterpolated_element 1 and then cube, which is, I think, cubic interpolation. And there's another comment. For x equals 0, this returns what? This returns p at position 1. Okay, what about this x? So we have, oh no, what about this p? I mean, const, then we have not a mat, but we have a const float star const p. And then we have a const float x. Not a width, not a y. That's all. So we basically have two floats. One seems to be an array and one seems to be just a singular value. Or a single value, not a singular. This has a different meaning. Okay. And then we have a long formula which I will write out first. So I define a float res is equal to p1 plus 0.5 f times x times parentheses p2 minus p0 plus x times 2.0 f times p0 minus 5.0 f times p1 plus 4.0 f. Let's turn on the music. Okay, times 4.0 f times p at position 2 minus p at position 3 plus x times 3.0 f times p at position 1 minus p at position 2, then closing parentheses, plus p at position 3 minus p at position 0, and then we have 1, 2, 3 closing parentheses and a semicolon. Okay, we can get rid of the rest and just return the res, the result. Okay, this is about 1 cube. Then we have another cubic interpolation. We'll copy and paste that. And this will be called get interpolated element 1, 2 cube, float const p, float x. Then we have several floats. Float c1 is equal to 0.5 f times p at position 2 minus p at position 0. And that's it for this line. Float c2 is equal to p at position 0 minus 2.5 f times p at position 1 plus 2 times p at position 2 minus 0.5 f times p at position 3. Next we have float c3 is equal to 0.5 f times 3.0 f times p at position 1 minus p at position 2, closing parentheses, then plus p at position 3 minus p at position 0, closing parentheses and semicolon. Then we have a float xx equals x times x, and we have a float xxx equals xx times x. Then we have an eigen vector 2f. And this will be called res, and this will be returned. This consists of p at position 1 plus x times c1 plus xx times xx times c2 plus xxx times c3. So this is the first entry, it seems. The next entry is c1 plus x times 2.0 f times c2 plus xx plus xx times 3.0 f times c3. And this is the second entry, the second dimension. And this should be it. So next we need another cubic interpolation. Which is called get interpolated element 32 cube, which returns a vec, an eigen vector 2f. Actually, the one above should return the same data type, not a float. So the most recent two functions return a 2D vector, but this function takes in a 3D array. So we change this const float to a const eigen vector 3f, const p, const float x, And we calculate C1, which now is the 0th element of P2 and the 0th element of P0. Then we have C2 is equal to the 0th element of P0 minus 2.5 times P0 element of P1 plus 2 times 0th element of P2 minus 0.5 times 0th element of P3. So we basically only add some zeros here. Okay, the rest is the same. And in the result, we also need to add a 0 here. Then plus x times C1 plus xx times C2 plus xxx times C3. And then we have C1 plus x times 0.2 times C2 plus xx times 3 times C3. Okay, looks good. Now we can copy that again and paste it here. And this one will be a bicubic interpolation. So this will be called get interpolated element 1,1 bicube. Then we have a float as a return type. And as the name suggests, we also have a float star, and this time a const mat, const float x. Now we have once again the const float y and probably a width. Const int width. Okay. Here we once again need the functionality from above. I will quickly steal that. The first 3 lines here at least. Okay, so in the get interpolated element 1,1 bicube, we start with this integer part ix, iy as we did before, and then we need a float dx is equal to x minus ix. Then follows a const float star bp is equal to mat plus ix plus iy times width. Then we prepare a float val array with 4 elements, where we fill up val at position 0 with a function that we have implemented before, which is get interpolated element 11 cub, and then we have bp minus width minus 1 dx, and we copy that 3 times, set val 1, 2 and 3 by changing bp minus 1 dx, then bp plus width minus 1 dx, and bp plus 2 times width minus 1 dx. Next, we calculate float dy is equal to y minus iy. And we now just need to return the get interpolated element 11 cube val dy. Simple as that. So we are already using the function that we have implemented before. So now this is the time where this comes in handy. Okay, now we copy that function and paste it. And this function will now be called get interpolated element 1, 3 by cube, and it will return, as the name suggests, eigen vector 3f. It will take in a const float pointer to const mut, then const float x, const float y, and const int width. Then it will get the integer parts for I, x, I, y. dx is the same. Then we have const float bp equals mut plus ix plus iy times width. Then we have float val4, and we also have float grad4, which is probably the gradient, I would suppose. Then we say eigen vector 2f v is equal to get interpolated element 1, 2 cube from bp minus width minus 1 dx. Then we say, I see. Okay, then we say val1, val0 is equal to v0, and similarly grad0 is equal to v1. Then we are reusing v with get interpolated element 1, 2 cube with bp minus 1, bp minus 1 dx. Then we fill out val1 and grad1 with v0 and v1 again. Then we copy that. We call the same function with bp and now plus width minus 1 dx. And we fill in val2 and grad2 with v0 and v1. Next, we call the same function with bp plus 2 times width minus 1 dx. We fill in val3 and grad3 with the same values. And then we calculate float d, I think I have it here. Let's get rid of that. Then we calculate dy is y minus iy, and we calculate another v. V equals get interpolated element 1, 2 cube of val dy, and then we return eigenvector 3f with v at position 0, get interpolated element 11 cube with grad and dy, comma v at position 1. Okay. If this is not error prone, I don't know. Okay, then we copy that once again, the whole function. And we call that get element 3, 3 by cube. And we change this float to eigenvector 3f with a constant mat, float x, float y, and constant width. Okay. Then once again we get the integer parts. This is the same. Then here we do not have a float but an eigenvector 3f, bp mat ix iy width. Then we have the val grad. Then we have the 2D vector f, v equals get interpolated element. And now we have to change it to 3, 2 cube, but the rest seems to be the same. So let's copy that and paste it here for the other 3 calls. bp minus 1 dx, bp plus width minus 1 dx, bp plus 2 times width minus 1 dx. The rest is the same. Now what about this part? dy is the same. V is equal to, now we have to pay attention, this is get interpolated element 1, 2 cube and not 3, 2 cube, val dy. Then we have eigenvector 3f, get interpolated element 1, 1 cube, grad dy, v1, and this is it. Okay. Next. We are not finished yet. Next we have a similar function but much shorter. So let's copy that and paste it here. So the next function is returning a vector 4f, and it's called get interpolated element 4, 4. Therefore we need to input a vector 4f mat, const float, const float, and const int. Okay. We again get the integer parts, calculate the dx. We also need to calculate the dy here. Oops. And we need to add this float dx dy is equal to dx times dy. Then we have a const eigenvector for f mat ix iy times width. Okay, that's fine. And now we return a vector for f and we call it res again. So that we can return it here. And now we need to fill in the parts. Which are fortunately only a sum. So dx dy times, in parentheses, bp plus 1 plus width. So this is the first part. Then we add dy minus dx dy times bp plus width plus dx minus dx dy times bp plus 1 and lastly plus 1 minus dx minus dy plus dx dy times, in parentheses, bp. Okay, next we return the result. And we are finished with that function. However, this is not clear if this is a bicubic interpolation. So let's delete this comment and let's continue. We now copy that function once again. And we want to return a vector 2f. And therefore, we call it getInterpolated element for 2. We still get a vector 4f mat as input with all the other arguments. We get the integer parts, dx dy and dx dy multiplied. Then we return, or we store a vector for f here, okay. And now we can create our results, which should be a vector 2f in this case. Let me quickly double check, yeah, okay. So we return dx dy times, and now we need to have, I see, we need to add a new parenthesis here, const eigenvector to f star And this is what we need to add to every line. Like this, but we have to return this star. Same here. BP plus 1. And this should be fine as well. Okay. This should be this function, and we return it. Let's double check. Okay. Now we are actually finished with the interpolation function. So now we have visualization. Color ramps, I would say. That is, let's create this fancy divider. Generate colors for visualization. This is an inline function which returns a vec3f and is called MakeRainbow.h, capital F. It takes in a float ID, and here's the body. First, we define the ID to be multiplied by the free debug param3, semicolon, and we check if the ID is less than 0. If this is the case, then we want to return a vec3f with values 1, 1, 1. ID is less than 0. Okay. Else, we create an integer ICP, capital P, is equal to ID. A float IF, capital P, is equal to ID minus IC, capital P. And IC, capital P, is equal to IC, capital P, modulo 3. Then we check if IC, capital P, is equal to 0. Then we return a vec3f, which consists of 1 minus IF, capital P, comma, IF, capital P, time, comma 0, semicolon. We copy that 2 times because we want to check IC, capital P with 1 and 2. And in the case of 1, we want to return 0, comma, then 1 minus IF, capital P, comma, IF, capital P. And then with 2, we want to return IF, capital P, 0, and then 1 minus IF, capital P. Like this. Then we assert false. This is useless, this statement, but okay, I will leave it here. Return vec3f 1, 1, 1. Let's create a to-do. Okay. So now we have MakeRainbow F3 capital F. We copy that and make a new version, which we call MakeRainbow without F3 capital B. Once again, it takes in a float ID. Okay, the same. And if not the ID is greater than 0, then we return a vec3b with the values 255, 255, 255. So this is obviously an unsigned int, unsigned char probably. And therefore I need to change this return type from vec3f to vec3b. Okay, now this is returned. ICP is the same. IF capital P is the same. Modulo 3 is the same. Then we have the ICP. Oh, that's actually quite funny. ICP. Return vec3, not F, but B. This is the case everywhere. Fortunately, not an assert anymore here. And now this needs to be changed to be this float value here times 255. So every value needs to be multiplied by 255 unless it's 0. Like here. Okay. So this is about the rainbow colors. And now we have the same function as with the rainbow. We copy that, paste it, and rename it MakeJet3B. Okay, float ID is still valid, but this free debug param is not valid anymore, so remove it. We check if ID is less than or equal to 0, then we return vec3b with 128 and then 0, 0. And we have another check. If ID is greater or equal to 1, we return vec3b with 0, 0, 128. Then we have the int IC. Then we have ID times 8. Wherever this 8 comes from. ID times 8 minus IC. IFP. Okay. So this can be deleted. And now there are quite a few of if statements. Now I see why this is at times 8, because we have 8 kind of color, individual colors, I would say. So let's quickly first adjust the first 3, 0.5 plus 0.5 times IFP, and then we have 0, 0. Okay. Here we have 255 times 0.5 times IF capital P and 0. Then we have 255 times this expression, comma 0. Okay, and now I will turn on the music again. And now we add the other if conditions, which means we have to change this to 3, 4, 5, and then we have 6 and 7, and that's it. And with number 3, we have this 1 minus 0.5, and then 255, and this one 255 times 0.5. Okay. Then we have 255 times 0. It should be this one, number 4. Okay, but this should be a minus here. 0.5 minus 0.5 times IF capital P, and then 255 times 0.5 plus 0.5 times IF. And the comma 0 can be deleted. Now we have a 0, comma 255. Then we have 1 minus 0.5 and 255. At number 6 we have 0, 255, 0.5 minus 0.5 and 255. Okay, and lastly we have 0, 0, 255 times 1 minus 0.5, and let's delete that. Okay, And if all those if conditions will not evaluate to true, then we return white. Okay. Next we will copy that again. But this will change quite a lot, because here we have we return an unsigned char again, but this function is called make red green freebie, which takes in a float called val. There's a comment: 0 equals red, 1 equals green, and 0.5 equals yellow. Okay, those are interesting functions, I have to say. If val is less than 0, then we return 0, 0, 255. Next we have an else if val is less than 0.5, then we return 0, 255 times 2 times val, and 255. Then we have 2 times more if statements, else if val is less than 1, and we have an else. So if val is less than 1, then we return 0, 255, 255 minus 255 times 2 times val minus 0.5, like this. And else we return just green. Okay, the rest can be deleted from this function. Okay, lastly, we have a new function, inline bool eigen test none, which takes in a const mat xx and m, comma, standard string message, where we define a bool which is called found none is equal to false. Then there's a for int y equals 0, y is less than m.rows, and y plus plus. We copy that and put it into this code block, because here we loop through the x's. X is less than m calls and x plus plus, and then we test for if not standard is finite. Then double cast to double m at y comma x. Okay, and if this is true, then we set found none to true. Okay, then after the for loops, we check if found none, if this is true. Then we want to print something to the screen. That is none in message.cString and we'll return found none. Okay, now there is a log warning. Okay. This colon here is very weird, but okay. Good. We are finished with this file. So we can save it. And we'll try to compile. This is the compilation. Okay, we have an error. Of course, once again, a semicolon is missing. Global funcs 36. 36. Yep. Okay, what else? Nothing, fortunately. Good. Okay. Did I try what happens if I try to run it? Ah, still the resolution, yes. Okay, of course. Okay, good. After almost 2 hours, we are done with that. Okay. Now let's see. We still have left to implement ImageRW and ImageAndExposure. Let us take a look at how this is done. ImageRW. Okay, this needs the minimal image, but we can start with that. I would say we try to finish at least this file, if not even this one, and we will continue with undistort the next time. Okay, so we need a new directory, which is called frontend in the include directory. So include frontend. Then we make a new file, which is called ImageRW.h. Alrighty. So we once again start with pragma once. We write the include guard. If not defined, LDSO Twitch ImageRW.h. We want to define it. And here we end the if. Okay, here we include our favorite num types, and we also include the MinimalImage.h. I define a namespace, LDSO. There's some weird thing happening. And inside the LDSO namespace, we define namespace IO wrap. And in this namespace, we define a minimal image B pointer read image BW 8U standard string file name. Then we have a B3 read image RGB 8U standard string file name. Then we have a minimal image unsigned short star read image BW 16U standard string file name. And we have a minimal image B read stream BW8U standard, no, not standard string, but in this case we need char star data, pointer data, int num bytes. And then we have several functions which return void and are called write image, taken a file name, and a minimal image B star img. And we need to have them for the different file types, which is B3, F, and F3. Those are the images. Okay, and that's it for this header file. Let us now implement the CC file, I would say. So we get to the source files, here source, and in source we need to create this new folder, front end. And in front end, we'll create a new file which is called ImageRW.h. ImageRW, but we add OpenCV.cc here to designate that we are using OpenCV as the image backend. Let's copy that part from the header file. And let's move it here. Or paste it here, I mean. And of course we want to include here something. Include frontend ImageRW. But we also want to include OpenCV, for in my case, OpenCV2 core version HPP. Then we have a preprocessor directive if defined CV version epoch and CV version epoch equals 2. Then we want to include, so this is some compatibility measure. High GUI. Else we want to include IM codecs, IMG codecs, IMG. And then we end if. IMG codecs is not available. This is weird. Okay, we might have an error here because OpenCV is not loaded, but this should not be a problem. Okay, now let's implement the functions here. So in IOWrap, we have this MinimalImage.b, read image bw8u, string file name. Now we add the implementation here. We do that everywhere so that we don't forget it later. Okay. Here we need to get CVMat. M is equal to CV IM read file name and CV IM read grayscale. Next we check if m.rows times m.calls is equal to 0. Then we know that we have a log error CV IM read could not read image file name. Exclamation mark, this may seg fault. End line. but we return a 0. Next, we check if mType is not equal to CV8U, then CVIMRead did something strange in the neighborhood. This may segfault. And lastly, when this passes, then we get a minimal image B star img is equal to new minimal image B m calls m rows. Then we make a mem copy img data m data m rows times m calls. Then we return img, and this is this function. Okay, for the next function, things look quite similar, so we can copy that. The only thing is that we are reading an RGB image here, so we need to change this to IMRead and then color. The rest can stay exactly the same, but there is an issue here. CV8UC3 should be an unsigned char 3. Then we have a minimal image B3. IMG is new minimal image B3. M calls rows. Mem copy data. M data. And here we have 3 times M rows times M calls. And we return the image, and that's it. Next is also quite the same. Read image BW16U. Met M is CV IMRead. IMRead unchanged. Then M rows, M calls. Could not read. And the type is now CV16U. And here we print the message read image BW16U called on image that is not a 16-bit grayscale image. This may segfault. If this passes, then we have a minimal image not B, but unsigned short with new minimal image, unsigned short like this, Then we have memcopy data mdata 2 times rows calls. And this is it. Lastly, let's copy that once again. For the read stream. And here we need to ImRead, ImDecode, we need to change that, yeah. Then we have CVMat numBytes 1 CV 8U data, comma, CV ImRead, and we read in a grayscale image. Okay, then we have same, but CV ImDecode could not read stream. And here we say that we have numBytes bytes. This may segfault. We have 8-bit unsigned char. And we say that here once again, CV ImDecode did something strange. This may segfault. And if this passes, then we say MinimalImage B img is new MinimalImage B. Memcopy image data mdata mrows times mcalls return img. Okay, and the write image is a lot easier. Because here we say CV ImWrite file name CVMat ImageAndExposure.h img width CV8U and img data. Don't forget about the semicolon. And now what we need to change is just the data type, which is 8UC3 here for the RGB image. It's a CV32F for the float image, and it's 32FC3 for the float RGB image. Okay, and this is the implementation of the reading and writing of images. This CC file needs to be added to the CMakeLists file, as we did with the global calip. So let's not forget about this. We have a front end folder, and we have ImageRW OpenCV.cc. And slowly, this CMake lists text is filling up. So that we can hopefully soonish process our images. But we are still missing something very important, which is the MinimalImage.h. So let us quickly check first maybe if this compiles. Oh no, it will not compile because we do not have this minimal image. So let's first try to get the minimal image here. And minimal image seems to be a header only file. So we need to add it here. It is located in the front end. So let's add this new file, MinimalImage.h. MinimalImage.h. This file will have 108 lines. So let's start with implementing it. I will just copy that part. And this is the LDSO Twitch minimal image. Like this. Or maybe like that rather. Okay, here we want to include the algorithm, and we want to include our happy numtypes.h file, and we want to use the namespace std, and we want to define a namespace LDSO. And here we will create a new templated class. So we start with the template of a type name T, and next we write the class for the minimal image. And there should be a semicolon in the end. And after this class definition, we add some type defs for eigen matrix unsigned char 3x1, which is a vec 3b. And we also add a type def for minimal image of type float for minimal image f Then we have a vec3f for MinimalImage f3. Then we have an unsigned char MinimalImage b. Then we have a vec3b for MinimalImage b3. And then we have an unsigned short for MinimalImage b16. 3.1. Okay, that should be fine. Okay. In this minimal image, we have two scopes. We have a public scope and a private scope. In the public scope, we first define eigen, make, aligned, operator, new for optimization purposes. Then we add a w integer and an h integer for width and height. Then we have a data type for the data, obviously. Then we have constructors, different constructors. This one is one that creates minimal image with own memory. And the next one will be one that creates an image wrapping around existing memory. Let's add constructor here to make it clear. And there will also be a destructor that will hopefully clean up its own mess. And now let's implement that. So the first constructor will be defined inline. Minimal image in w dash or underscore, I mean, int h underscore. And then we initialize w by w underscore and h by h underscore. The data will be set to new t of size w times h, and own data will be set to true. We will define the own data variable in the private scope. But first, let's create the other constructor. This one takes in a width and a height and also a data type for the data. And width and height will be initialized. Data, however, will be set to data underscore, and own data is false. Okay, for the destructor, inline minimal image. The implementation looks like this. If own data then we want to delete an array of the data. Then we also want to have a method which returns a minimal image pointer, which is called getClone. And this one creates a new minimal image clone pointer to new minimal image of width and height. Then does a mem copy of the clone data size of t times w times h, and it returns the clone. Okay. Next we have variables to return the color, or basically the data type that represents either the color or the intensity, which is inline data type t and at int x int y, and this just returns the data at position cast to int x plus cast to int y times w, semicolon. And we also have one variant which says that it just gets an index I and returns the data at this index I. Next, we have a method inline void inline void, which is called setBlack, which does the following. Somehow this indent is off here. Sorry about that. Okay, setBlack does a mem set of the data with 0 with a size of t times w times h. We can also set a const when we pass a value of data type t. where we loop through and I equals 0. I is less than W times height and I plus plus. And for every little entry or little pixel, I would say, we set the value to val. Then we also have the possibility to set a pixel, set pixel 1 to a const float u, const float v, and a tval by just calling at u plus 0.5 f, v plus 0.5 f is equal to val. Which is an interesting way of writing it. Okay. Set pixel 1. This will set 1 pixel. Okay. If we have this method, then we can, of course, also set pixel 4. Why ever this should be relevant, where we can set 4 pixels by adding 1.0 f to u and v, and also to u only, and also to v only, and to no pixel at all. So this one will basically set the 4 neighbors to a specific value that was passed. Next, we also have set pixel 9, which will do a similar thing, but at more positions. Let's copy that. So the first one is u plus 1 and v minus 1. Then we have u plus 1, v, u plus 1, v plus 1. Then we have, oh, it was the next, okay, u and v minus 1. Then we have uv, u and v plus 1, u minus 1, and v minus 1, u minus 1, and v, and u -1 and v plus 1. Those are 9 entries, should be correct. Okay. Now we have something fancy, because if we can set neighbors, then why not set the pixel in a circ, which probably means circle. And that is, we execute a for loop with int I equals -3. I is less or equal to 3 and I plus plus. And then we call different methods, namely 8, where we set them with +3 and v plus I. So the last one is always v plus I in the first block. And in the second block there's u plus I here. Okay, here it starts with u plus 3, u minus 3, u plus 2, and u minus 2. And here it is v minus 3 and v plus 3, v minus 2, and v plus 2. The rest can be deleted. And in the private scope, we add a bool called onData. And with this, we should be finished with the minimal image, which is the very important part to actually store some pixel values and be able to visualize them. So here we have the minimal image in the ImageRW. So it's using the minimal image, I would say. So the minimal image is included in the ImageRW header file. And this should be fine now. Okay, so we can go to the dataset reader now and uncomment the ImageRW so that it is used from now on. And what about the image and exposure? Let me quickly check. Image and exposure. Image and exposure does not have an implementation file, so I would say we'll go ahead and add it as well. So we can remove it here. And let us create this in the front end. Let's copy the include guards. Okay, so here we have the LDSO Twitch image and exposure H file. And then we have a hashtag and if, and can create our logic here. Of course, what we want to include here is the num types. And we want to establish the namespace LDSO once again. And in this namespace, we want to create a new class called ImageAndExposure, which has a public section, public scope, where once again we have this eigen make aligned operator new. Weirdly enough, there is no semicolon for the for this macro here, but I think I will add it here. Added semicolon in contrast to original code base. I have no idea what kind of influence this has, but it seems good to have this here. I might look it up at some point. Image and exposure. Yes, we have this eigen make aligned operator new. Then in the class we have in the public scope, of course we need to have a float pointer to the image, which is a null pointer in the beginning. This is the irradiance between 0 and 256. In my view, this is wrong. Shouldn't this be 255 at max? But we will check that at some point. We have an integer w equals 0 and height equals 0. We have double timestamp equals 0. And we have a float exposure time equals 0. And the exposure time is in milliseconds. Then we have an inline constructor, image and exposure, int w, int h, double timestamp equals 0. We initialize that by putting W underscore and W, H underscore and H, and timestamp underscore and timestamp. Then we have our curly braces, where we set in the constructor the image to a new float array of size W times H, and the exposure time to 1. Then we have an inline destructor, ImageAndExposure, where we delete the whole array, the image, and free up the space. Then we have an inline void copy meta 2, which takes in an image and exposure, other image basically, and we say for the other image we take the exposure time and set it to our exposure time. And lastly, we have an inline function, an inline method, which returns an image and exposure, which is called getDeepCopy. In this method, we make a new image and exposure object, a pointer to an image, which we create using new image and exposure with a width, height, and a timestamp. Then we say for this image, we take the exposure time and set it to our exposure time. Then we copy, and this is where the deep copy part comes in. We copy from this IMG image the image data to the image with the width and height times size of a float data type. And then we return the image, which is then a deep copy. So we did not only copy the exposure time, but also the image data. Okay, the class should end with a semicolon, something I am always forgetting about. And this should be everything. Now it's definitely time to test if this works, or if we have a lot of problems, which I do not hope. So let's try to compile that once again. We make the project, and fingers crossed, we have errors. Here we have data which is not declared in the minimal image, but this is the only error, which is amazing. But let's try to fix it. So MinimalImage.h 38. MinimalImage.h 38. 38. This one. Okay. Maybe I have written something wrong here. Let me see. Yes, the constructor is wrong. This should be an underscore. Now this should be fixed. Now it's linking. Now it takes quite a long time to compile. And we are not even done by half of implementing it. But okay. There are some warnings about memcopy. I can take a look off camera if this is something which is a problem. Class matrix. Okay. Now let's try. If we load it, need a higher resolution, which is still okay because we do not have it, but it's not crashing at all. Now let's see if we go to the dataset reader. Let's see what we can do to at least test this functionality. We have an image and exposure, so I can comment in this part. And we do not have an undistorter, unfortunately, so until we get the undistorter, we cannot really test it. Unfortunately. But we can at least get image internal. Or we could at least read in the images, it seems, if there's not something really important missing. Image and exposure, this should be available. Oh, there's the undistorter here again. The bad undistorter. Which is not useful at the moment. This standard vector can be commented in. Yeah, let's try to at least comment in some of those files. Get image raw internal. Undistort. So this is not possible at the moment. It's not good to comment it in. I'm afraid we need to wait until we have the undistorter. We might be able to comment in this one. I'm not seeing anything that is a showstopper here. And this one should also be able to be commented in. Here's the undistorter again. Undistorter, undistorter. Okay, let's try it again. Maybe we can do something useful. Get image internal. Okay, there are some errors here. Dataset reader, the prep image. This one, there's no data type. Yes, I would also complain about that. Let's see. Ah, but it's a constructor. Prep. Ah, there's a type error, a typo. Prep image item. This should be correct. And then we have DatasetReader.h. 283. Get image internal. Yes, this is commented out. Get image internal. Maybe. Maybe I can, for now, define this as a null pointer. Will this work this way? Oh, yes. There's more code here. Let's see. Okay. Let's execute. Still not loading the images, of course, because the undistorter is still missing. But I mean, the images should still be loaded. Buffer still too small. Okay. It's not even loading the files unless the undistorter is working. Okay, I would say let's call it a day. The birds are chirping already, so let's stop here. The next time, in the next part, we will take a look at this front-end undistort header file and the implementation. And then I hope we'll finally be able to read in the images, show that we have pyramid levels calculated, we have resolutions, we have a calibration, and we are set to use those images for estimating the camera poses in the full system. We will see if we get to something more fancy next time. This time it was really a lot of work to get the basic things done, but I think being able to work with image data, seeing how it is all organized, that we have a minimal image, that we have an image and exposure, they are intertwined, and we need both of them to actually make our dataset reader running. And yeah, as I said, next time we will hopefully read in those images and display the resolutions. Thanks for watching and see you next time. Goodbye.